Hello, my name is Richard Lüpken. I'm from the Berlin Institute of Health, and today I will tell you about mapping linked read barcodes to a reference without performing a read alignment. So the first thing we would need to know is what linked read data are. And for linked reads, large molecules, as they would be used for long read sequencing, are separated into small batches or even singulated, depending on the method. And those large molecules are then sheared into smaller fragments as they would be used for short read sequencing. And they are then ligated and marked with a barcode. And then they are sequenced using a standard short read protocol. So this has the result that we have that reads from the same large molecule are always marked with the same barcode. However, it can be that multiple molecules can have the same barcode. And another result of this is that we have or not really a result, a property is that we have a low read coverage per molecule. So we can see this here in the picture. Taking one barcode wouldn't be enough to perform something like a read alignment, for example, like an assembly, for example. So as for pretty much all evaluation of DNA, we need to compare it to something. We usually compare it to a reference. And for that, it would be important to know where these large molecules originate. And if you know that, you can, for example, collect all barcodes that come from the same region and then perform an assembly. So we implemented a tool for just that. It's called BCMap. And as input, it takes paired end linked read data, currently from 10x Genomics, but support for other protocols will follow. And the barcodes have to be extracted and corrected, and the FASTQ files have to be sorted by barcode. So it looks like we see here on the right side. And also we need a reference to map those barcodes to. We then start by building an OpenAddressing KMA index for the reference, and then we use this index to map the barcodes to the reference and determine barcode windows on the reference. And while we're doing that, we're also constructing a barcode index. So the output is a bat file containing the best mappings for every barcode. And this includes the position on the reference, and of course, the barcode it belongs to, as well as a score for every mapping that tells us how trustworthy the mapping is. And also we return the barcode index that I mentioned before. And this can be used to quickly retrieve all reads belonging to a barcode or all reads belonging to a set of barcodes from the FASTQ files. So the first thing I mentioned is the OpenAddressing KMA index of the reference. And OpenAddressing indexes are state of the art, but for those who aren't aware of them, I will quickly explain it. We use, like a regular hash table, we use hashing for fast lookups, but unlike a regular hash table, the hashing is ambiguous. So there is not a position in the table for every possible KMA. So the workflow is as follows. We take the KMA, we calculate a hash value, and then we query that hash value. And now it might happen, due to the ambiguity, that the position in the hash table is already occupied by another KMA, and we would see this by this identifier. If this is the case, we have to rehash, and the new hash value will be based again on the KMA, but also on the old hash value. And then we would query this new hash value. And eventually we're gonna find the correct position in the hash table, and then we can extract all positions on the reference for the queried KMA. Now, this loop makes it so that the lookup time is no longer constant, as it would be with a regular hash table, but we can save on a lot of memory for the index. And by the choice of clever hash functions, we can reduce the amount of iterations of this loop so that the lookup still remains very fast. Another techniques that we used are minimizers. This is also quite standard. I will, however, quickly explain it. Minimizers offer a representation of a k-mer set through a defined subset. And for that, the base sequence is split into windows of length w. In this example on the right, this length w is 8. And then the smallest k-mer of every window is determined and is kept as the minimizer. And if successive sequences and windows have the same minimizer, then it is only kept once. However, in our implementation, we kept track of how often the same minimizer appeared in a row. And we will use that later on. So we can see in this example that the 14 formers of the original sequence are represented by just 4 minimizers. However, the order by which we determine which minimizer is the smallest does matter. And in the example, an alphabetic order was used, and we can clearly see that all minimizers we determined start with the letter A. So this is a strong bias towards a subset of k-mers. And in our OpenAddressing index, this might lead to a lot of collisions. So to keep the lookup times down, we went for a random order, and we achieved that by multiplying the bit vector that represents the k-mer with, not multiplying, we performed an XOR between this bit vector and a random bit vector, and then we took the smallest one. So we essentially got a random order, and by that reduced the amount of collisions. So now for the workflow of the barcode mapping. Using the read files, we collect all reads that belong to a single barcode. And we do that for all barcodes. So this is highly parallelizable because the rest of the workflow just works on one barcode. And while we're doing so, we are also creating the barcode index, which I will talk about later. And from this read set for a certain barcode, we take all minimizers and we query them in the OpenAddressing k-mer index. And then we retrieve the positions of those minimizers, but we just do that for rare k-mers that do not appear too often in the reference to keep the amount of data we work on small. We then sort these minimizer hits by their position, and then over these sorted hits, we use a sliding window and a score, which is calculated by the sliding window to determine the best mapping genomics windows. And this happens as follows. Here we see the k-mer hits, and they are classified into windows. And down here we see the score that is used to calculate the quality of the windows. And we have two break criteria. First of all, a maximum window size and a maximum gap size. So in this example, we see this lone k-mer hit here, which is hurting the maximum gap size criterion, and hence it does not belong either to window 1 or window 2. And over here, we see that this k-mer, if it would belong to window 3, we would hurt the maximum window size criterion. And this one, for example, was chosen over that one to belong to the window because in this constellation, we would achieve a bigger score. And for the score, it is very important how frequent a k-mer is. Very rare k-mers are weighted much higher than frequent k-mers. And also we take into account the active basis. So for how long the minimizer was active, for how many successive windows. And in the results can then be filtered for either the score. So we could throw out windows that have a too small score because they only are only based on very frequent k-mesh. And we can also sort out windows that have a length that is so small that we wouldn't believe that they resemble a large molecule from the linked read sequencing. And our other result is the barcode index. And in this, we simply have a table of all barcodes that are present in the data. And for every barcode, we have saved their positions in the read file, the start and end positions. And when we query it, we use a binary search. We can query it in log n time. And we then can extract from the read files all reads belonging to the barcodes in constant time in respect to the amount of reads that are present for this respective barcode. So we tested the performance of our mapping tool, and we compared BCMap to BWA and Long Ranger. So we compared them to complete read alignments. We did it for the NA12878 sample, and we mapped it to the HG38 reference. And we can clearly see that we are much faster because, of course, we're not performing the same task, so this is to be expected. But this was also a motivation to do this, to be much faster than a complete read alignment. And we can see that even running on a single score, we are still faster than the competition. However, it has to be noted that for Long Ranger, this time includes the pre-processing of the read data, so barcode extraction and correction, as Long Ranger only takes raw data as an input, and we had the data pre-processed for our tool and for BWA. And the index time construction, of course, has to be performed. The index construction only has to be performed once for every reference you want to use. So, and next we tested the accuracy, and we compared it to BWA. And here it is important to know, I will talk about false negative, true positive, but we are not comparing it really to a truth, but we rather look at an agreement with BWA, because BWA being a short read aligner, of course, it doesn't know the truth about linked read molecules. So for false negative, we defined it that if there are 10 BWA read alignments or more that cluster on the reference and we have no barcode mapping that resembles this, then this is a false negative. And for true positives, we define that if there is a BWA alignment that matches our mapping, then this is a true positive. And if there is no such alignment, then this is a false positive. And we did this calculation of recall and precision for several different score thresholds. And here we can clearly see that the higher the score, we actually have a better mapping. So the precision for higher scores gets much better, and the recall only drops very slightly. So a mapping with a low score can still be correct, but the higher the score, the most likely the mapping is correct. And another thing we looked at is the impact on W, on precision recall and running time. And W, if you remember, is the window size for the minimizers. And we performed this for K equals 31. So we see our first point here, W equals 31. The window equals the k-mesh size. So this is essentially the case as if we would not use minimizers at all. And we can clearly see that the use of minimizers and using larger windows has a big impact on the running time. It gets much faster, of course. But it has a very minor impact on only on the recall. It just slightly drops for larger windows, which is also to be expected. And for the precision, we cannot really see a clear trend here. It is kind of fluctuating. So I think we might take from this that there is no real impact on the precision using less, using minimizers from bigger windows. So finally, we can submit that we implemented a fast barcode mapping method, and we hope that this in the future might allow the efficient use of linked read information right from the get-go, because this is would be a very early step in the data assessment. And also, as expected, the approximate barcode mapping is substantially faster than a complete read alignment. That was kind of the motivation as well. But the results still largely agree with the results of a read alignment. And also, we have the barcode index to quickly access the barcodes that are mapped, or rather to access the reads that belong to the mapped barcodes. And this hopefully provides a good starting point for future analysis. And finally, the code and the tool is available on GitHub. Thank you for your attention, and thank you to all that helped me in this project.